Welcome back to EET 260. So this is week 3, and where we left off in week 2, we were looking at things like pulse width modulation and control of positional servos and continuous rotation servos, and we were using a pulse width modulation technique there to see if we could set a DC level by having fatter pulses or narrower pulses. The average DC level of a rectangular train of pulses will go up or down. Fatter pulses will have a higher average value, which is your DC value, and skinnier pulses will have a lower DC value. In the case of the positional servo, we were trying to build a driver for a motor that would drive a potentiometer around to a certain point. And you can kind of imagine that perhaps if the potentiometer were driven by a motor, maybe the potentiometer is hooked up one side to ground and the other to some voltage, let's just say 5 volts. And the center of the potentiometer may set a voltage because it's the wiper. It might set a voltage that maybe controls a train of pulses. And if we send a train of pulses to our motor that drives the motor to a certain position, we could compare it with either the DC level from the potentiometer, or we could compare it to perhaps a 555 astable circuit, that is just a continual pulse generator. But in either case, the motor could be made to drive to a position that the potentiometer then outputs a voltage, and we say, hey, we're there, we've reached that position. Or we could be still driving the motor because some circuitry that compares the potentiometer's output to whatever waveform is driving the motor says according to whatever algorithm and circuitry we're using here, it's not there yet, so we're going to drive it. Or maybe we've driven past it and it says we actually need to reverse direction and drive the motor backwards to the point where the input pulse train, using pulse width modulation, that input pulse train would be equal to some feedback we're getting from the sliding tap, or the wiper, as they say, on the potentiometer. The continuous motion servo was more of a speed control thing. As you put in fatter pulses, the motor would go faster. If you put in skinnier pulses, it would go slower. But there was a point at which if the pulses got skinnier, then the motor would stop, and if they continued to get skinnier, the motor would go the other direction. And if the pulses got skinnier still, then the motor would turn faster in the opposite direction. So in both situations, you have something controlled where you're comparing this input pulse train, and you're using the pulse width to cause the system to drive in some way in which you get feedback, and then you compare the feedback and you say, oh, we want to drive at a particular speed. In the continuous motion servo, it's a speed control, and you want to make the motor turn at some RPM, and you control that with a range of pulse width. Again, really skinnier pulses would cause the motor to go one direction. As they got fatter, the motor would slow down in that direction until it hit 0. Then as it went a little faster, as the pulses got fatter still, it would begin to turn in the other direction, and as the pulses got fatter, it would turn faster in the other direction. So positional servo and continuous rotation servo, at least the ones from Parallax, work as I've just described. We also talked about regular DC motors and the H bridge and how we could make the motor turn one direction or another based on the H bridge. And we talked about how pulse width modulation, once you set the direction by which two transistors you turned on or off, by turning those transistors on and off in a pulsed manner, you could make the motor turn in the desired direction more slowly or more quickly. So that's great. Pulse width modulation does a lot for us. And we may talk about some more things that you could do with motors, but we also have to look at where pulse width modulation allowed us to drive out a waveform that we could then kind of average out with a low-pass filter and get rid of those sharp edges, which are high-frequency components of the signal. Get rid of those. We could low-pass filter the signal, smooth it out, and get that average voltage. In that case, our pulse width modulated output could act like a digital to analog converter. We could select the duty cycle of the pulse width modulator, and after low pass filtering the output, we could make it we could make the average output be pretty near a DC level. It really could be a DC level if you put enough filtering in there. And so by specifying the duty cycle, let's say we had a 0 to 5 volt pulse train at 100% duty cycle. The pulse never goes low, and you've got 5 volts out. At 0% duty cycle, the pulse never goes high. You've got 0 volts out. And at 50% duty cycle, the pulse is high half the time, and the average voltage output is 2.5 volts. So depending on what the percentage duty cycle is, you can, with adequate filtering, come up with a DC level. Now in the case of motors and some loads, the loads are so slow to respond. Motors have a lot of inductance, and magnetism takes time. And so sometimes you can just drive them with the pulse width modulated drive signal directly, and they'll do the low pass filtering themselves, if you will, and so you can make an LED less bright or more bright. We did that. You can make a motor turn faster or slower. We did that. And to our eyes, at least, it all looked like it was a smooth, continuous control, but it was pulse width modulated. Okay, digital to analog. That's an output thing where we can get an analog drive signal because the outside world may well require it. Sometimes we need to do analog to digital. Now, in the case of digital to analog going outwards, you can get hardware. Sometimes a microcontroller will include hardware that will actually get you a lot closer to an output level with a digital number, and they call those digital to analog converters, and they're a unit that can either be an external integrated circuit, or it can be a part of your microcontroller, one of the peripheral circuits included in it. By the same token, you can have an input that is an analog to digital converter, where you take this outside world analog signal and you convert it to a number. So the basic stamp does not have this capability. It does not have a built-in analog to digital converter, but sometimes you can trade off time as a factor. So let's take a look at a couple of circuits here. In the first circuit, I'm going to turn on a power supply for 100 seconds and then turn it off for 100 seconds. That's what this guy does. And with current going through this resistor, now if you've had any experience with capacitors, you know that capacitors don't like changes in voltage. That's because you have to charge or discharge the capacitor. There's static electricity built up in this capacitor structure. There's an electric field in here, and so when you first go to pump charge into this thing, it goes in really quickly. But in this case, we're using a 7.5 volt supply. The charge goes in really quickly at first, but as the charge builds up, so does the voltage on the capacitor, and I don't have 7.5 volts to charge it anymore. I have a reduced voltage because the capacitor is charging up. And by Kirchhoff's voltage law, I have less voltage now across the resistor, so less current. Voltage divided by resistance is current. So this builds up and I get less and less current flowing in here, and it behaves in an exponential manner, not unlike some models of, say, like how temperature builds up in a room or in a temperature chamber or something. At first you can warm it up quickly, but then when the thermal gradient gets less, it's harder to get the next few degrees of temperature increase. So we're going to see this circuit charge, and you'll get an idea of this waveform that you see as this thing charges. And that's over here. The red waveform is the power supply itself. It just goes from 0 to 7.5 volts, bang, and but it takes us really almost 50 seconds to charge this thing up. And that 50 seconds comes from a couple of things. The product of the resistor and capacitor here sets a time constant for this exponential growth here, and to say it's exponential, it's exponential in a way. So what happens is this product, 10,000 times 1,000 millionths of a farad. So 1,000 millionths of a farad is really 1 millifarad, or 1,000th. So 10,000 times 1,000th, the thousands and the thousandth cancel, and I get 10 seconds as my time constant. And the rule of thumb is that from the mathematics on this, at about 5 time constants, you've really just about gotten it charged up. Or if you were discharging it, it would take about 5 time constants to get it discharged. And there's 5 time constants. There's 50 seconds right there. And you can say, yeah, there's a little bit left, but boy, you're pretty much there. So as we charge this thing, the charge builds up, the voltage builds up very quickly in the capacitor, and therefore the charge does, because voltage in a capacitor is proportional. The charge in a capacitor is proportional to the voltage. Okay, so as I'm able to ram in a lot of charge, then the voltage is going to go up pretty quickly. But as it gets harder, I have less and less voltage left to charge the capacitor, and that's why you get this tailing out behavior. So that's an RC, resistor capacitor charging circuit, and that's great. It shows you this behavior of how things charge, and maybe you've seen this in your courses before, not sure. But this is a discharge circuit. It looks a little complicated because I'm running it in a simulator, and what I do is this power supply here just programs this switch. I still have 7.5 volts that I'm using for my main power supply. I will turn this switch on for a brief instant because with no resistance here, I can charge this capacitor very quickly. In simulation, this 7.5 volt supply can supply infinite current, and that's the beauty of simulation. You can do things you can't do in real life. That's also the curse of simulation, because you can fool yourself into thinking a circuit simulates beautifully and in real life it doesn't. But in this case, trust me, I totally know what I'm doing. Famous last words. But I'm going to turn the switch on for a short bit. The power supply is going to charge the cap right up. Then we'll shut the switch off. All right. And the only place the charge from the cap can go, the capacitor, is through the resistor, and this voltage will decrease quickly at first and then more slowly in a way that you'll see is very much related to this charging curve over here. So we run this simulation. Here's a little pulse. This basically says turn the switch on, turn it back off. So as soon as we turn the switch off, the voltage starts dropping on this capacitor, and it eventually gets down here. At 50 seconds we're here. Let's see, maybe I think we had it on for 1 second. Yes, we did. So at 51 seconds we'd be about there. We're very close to, we're down like 1/10 of a volt or something out of 7.5 volts. So there's your discharge curve. Now we can actually put some cursors on here, and we can move this up. If you remember when we tested the input threshold on the basic stamp digital input, I thought we had something like 1.4 or 1.45 volts or something like that. So let's set this at 1.45, and it says here that that it should take us about 17.4 seconds to get there. But remember, 1 second was used in charging, so about 16.4 seconds to get there. So let's take a look at our circuitry over here, and what we have is a volt ohm meter, an analog volt ohm meter. The beauty of which is that we get to see the voltage go up or down. And let me set up my little stopwatch on my phone here so that we can time this discharge. Oh, I didn't realize that you couldn't see it. Maybe I can set the brightness down on that. And is that any better? Boy, it's pretty tough. I can get it. I make a little bit dimmer yet. So there you can see my timer. So what I'm going to do here, my power supply is just something from a wall wart, they call it over here, something you plug into the wall and it gives you power. And what I'm going to do is I'm going to hook up this thing. Oh, I lost my connection. There we go. So as you can see on my old meter here, I am right around 7.5 volts, and if you look at the meter closely over on the right hand side of the meter, you'll see DCVA, meaning those black scales are for DC volts and amperes. So our scale, although you can't see it, our scale is set for 10 volts. Or at least I can't see. Yeah, there you can see it. I'm sorry, I was blocking the light. So you can see that our meter scale is set for 10 volts, and you can see this DC volts ampere here. So we're looking at this black 10 volt scale, and I have set this to about 1 point. Let's see. No, I don't have that right. I have it down to what looks like maybe 1 volt. Let me, that's going to start discharging now. Let me see if I can set this a little better to 1.5 or 1.4 volts. So I think I've got that thing pointing better now. Perhaps if I move the camera more directly over it, it'll look, yeah. So, that's still looking like 1 volt. We want to get down to now. Let's look at it. Here we go. That looks a little better. I'm 1.2, 1.4, somewhere in there. So as I charge this thing up, let me get my stopwatch ready. Let's see how long it takes our circuit. Here we are. We're back up at 7.5 volts. Let's see how long it takes it to reach our kind of 1.4 volt point there. Now, we wouldn't want to put 7.5 volts into the input of our basic stamp. Don't do that. But I just picked this voltage because in a 5 volt system, this is where the basic stamp's input threshold would change. So I'm going to take this off, and I'm going to start the meter at the same instant. So there we go, and I'll try to stop the thing when we hit there. So we went about 16.4 seconds. I'm surprised it came out that good. I think maybe I've got an extra tenth of a volt in there. Other times I've tried this, it came out more in the 15.5 second area, but 16.4 is exactly what we were hoping to achieve. I doubt that's exactly correct. I think maybe that we're pointing closer to 1.2 than 1.4. So, but you get the idea. Now these components I have here, right now, what I have is I have a 10k ohm resistor and a 1000 microfarad capacitor right here, and they're in parallel, and I was connecting it here with the power supply, and we can do it one more time. We'll reset this and let's see how we do. I'll move this down here. So we go up there, and we start this, and maybe we'll stop at a whisker before. I don't know. I'm having such good luck. I'll do it at the same time, and this will come down, and we will. Oh, I stopped a little early, but 16 seconds. So you can see we're not bad on our timing, according to the mathematical models, but our components, the resistor is plus or minus 5%. The capacitors are maybe minus 10% to plus 20% or something like that. So they can be all over the place. But you can see that we could measure this resistance by driving this output, say, to 5 volts with our microcontroller, and then watching the same line on an input. And when the line changed at 5 volts, the input would be a 1, and then it would eventually, once you went down below 1.45 volts or something like that, it would change to a 0. If we could time how long it takes for this wire here, after we charged it to 5 volts, to sink all the way down to 1.4 volts, and we did a little bit of calculation, we could measure the value of this resistor, because or if we knew this resistor, we could measure the value of this capacitor. So in that way, those are analog quantities out in the world that we could measure with a digital system by using time, and the fact that capacitors and resistors have this nice decay characteristic. For the last part of this, I'll just show you a spreadsheet that I posted in the week 3 reading section on Blackboard. And this is set to, right now it's set to about, it's really more like 1.5 volts. And this one out here is at, well, probably a whisker over 16. It might be 16 point whatever, like we found. But mathematically, and I've put the equation up here for how this works. I've got a 10,000 ohm resistor, and I've got a 1,000 microfarad capacitor. My starting voltage is 7.5 and my ending voltage is 1.4. And these data here, I'm just doing, I'm putting in 0 seconds, and I increase by half a second on each line here. And here I actually compute, you can see an EXP in there, that's part of this equation. Here I compute the decay voltage according to this formula, and I come up with a time. You may have to look at this in your own on your own computer, but let's see, we can zoom in on this, and it's twice as big. If I go down here, hopefully you can see that that would be 17 and a half, so that's about 16 and a quarter maybe seconds. So we're right in the ballpark for what we said. So our mathematical model is set in a way that the laws of physics control that, but our actual experience out here was in the like 16.4, 16, 15.5 seconds, something, I don't know, whatever it is we've seen out here. And so we've seen the decay time on this capacitor behave like that, and we can use decay time to measure resistance or capacitance, whichever one we don't know. And that's a form of analog to digital converter. And if we knew both the resistor and the capacitor, the other thing we might be able to measure, suppose when we charge that capacitor up with an unknown voltage, then we controlled the charging of that capacitor so that we could disconnect it. We could watch the discharge curve and then time it, and from the timing number, figure out how much voltage was on that capacitor before it discharged down to 1.4 volts or 1.44 or whatever that input threshold is. Okie doke. We'll see you in the next video, and I'll post some things related to lecture 1 here in week 3's readings, and week 3 will also have some homework. So Thanks for watching, and we'll be back soon. Bye.